Today let us discuss about subgraphs and removal of vertices and removal of edges from a graph, and then we will see what are paths, simple paths, and then when do we say a directed graph is strongly connected or weakly connected, okay, and how to find whether a graph has a path of length n or not. Okay, so these are the things we are going to see today. Alright, and also I'll explain when do you say a graph is connected, and we will see cut vertices of a graph, of a connected graph, and then connectivity of we're also going to see vertex connectivity. Okay, so these are the things I'm going to discuss today. Alright, so let me start with a path. Okay, before that I told I'll discuss subgraph. So let's assume that G equal to V comma E. Okay, assume that this is a graph. Now subgraph is nothing but we're going to denote with H, that is W comma E, W comma F, where we say this H is a subgraph of G if W is a subset of the vertex set V and this edge set is a subset of the set F, the set E. Okay, for example, let me take this graph. So this is the graph between A, B, C, D. Okay, now it's a subgraph. I'd like to draw one subgraph of it, right? So that is what this A, B, C. Okay, so now this is the graph G and the subgraph is given here H. Alright, you see that there are 4 vertices in G and I am taking a subset of this vertex set, that is A, B, C. I am not taking all vertices in this H. Okay, in G. Now, how about edges? Actually, G has 1, 2, 3 edges. Okay, here I am taking only 2 edges. Anyway, I am not taking the vertex D, so I am not considering that edge. Right? So this is a subgraph of G. Okay. Suppose if you have an edge here, let's say if you have an edge from A to C, this cannot be a subgraph of G because the edge AC is here, but AC is not there in the original graph. Therefore, this edge cannot be a subgraph of G. Alright. Now let me give you one more example of the subgraph. Here I am taking 3 vertices again. That's it. A, B, C. This is another subgraph of G. Okay, if you want, you can take the other vertex D also. Fine. So this is also a subgraph of G. Even if I take this line, this edge, this also becomes a subgraph of G. Okay, it is not mandatory that we need to write vertices in this way. You can change the vertices. Let's say you can take A here, you can take B here, and C and D here, like this. Okay, but we will assume that the A here is same as the A there. Okay. So it seems there is some question. What is it? Can we say every graph is a subgraph of itself? Yes, we can say that every graph is a subgraph of itself. Why? Because in that case what happens, this W equal to V, F equal to E. Okay, so now every graph is a subgraph of itself, and moreover, let's see if H is not equal to G. Let's say H is a subgraph and it is not equal to G. where H is a subgraph of G. Now what we can say is this H is a proper subgraph. In this case we call H is a proper subgraph of G. If we mention H is a proper subgraph, it means that H is not equal to G. Okay. It may happen that you may not be considering the all vertices, or you may not be considering the all edges. Okay, even though if you consider all vertex, you're not considering all edges. That is what it means. Now let's look at these two graphs. Okay, so the vertices are nothing but corners here: A, B, C, D, E, F, G, H. These are the vertices. I'm taking a graph here, and I'm taking another graph. So this is one more graph I'm taking. Here the vertices are named as, okay, capital A. Let me name it with capital A, or we can go with X, Y, Z, W, and S, T, U, V. Okay, so these are the vertices we are taking. Now, so we can draw many subgraphs of these graphs. There are two graphs now, right? And we proved that, okay, I do not denote with H because I'm using the notation H for a subgraph. Okay, so let me name this as G1. Now this is G2. There are two graphs. Now my interest is to construct a subgraph given by the vertices of same degree. Okay, so here in the graph G1, you can see there are 3-degree vertices and 4-degree vertices, and of course there are 4 3-degree vertices, and here there are 4 2-degree vertices. Okay, now I'd like to see the subgraph given by 2-degree vertices. So what is the subgraph here given by 2-degree vertices for this one? So max you can take F, H, and here you can take B, C. Alright, so now there is an edge between F and H, and there is an edge between B and C. Okay, whereas let me take the subgraph of this graph, which is which is created by vertices of degree 2. Okay, what are the vertices of degree 2? I hope you can see it here. This Y is of degree 2. So Y, T, U, Z. Okay, so now let me see this. So one, I'll take Y here, and then actually degree 2 vertices are not connected here. Okay, I can simply write it like this. That's it. This is the subgraph given by degree 2 vertices, because no degree 2 vertex is connected to a degree 2 vertex here. Okay, Y is not incident with a degree 2 vertex. Even T is not incident with a degree 2 vertex. Similarly, U and Z, they are not incident with degree 2 vertices. Okay, so now if you see the subgraph given by degree 2 vertices, this is what? Null graph. We got a null graph. It means there are only vertices, but there are no edges. And whereas here, this is not a null graph. Okay, in the subgraph, the degree of F is 1 and the degree of H is 1. And similarly, B and C are also 1. But here, in the subgraph of G2, the degrees of vertices are 0. Okay, now using this, I can say that these two are not isomorphic. Suppose if the graphs are isomorphic, okay, now you construct a subgraph given by same degree vertices. then they must be similar. I mean, again, they must be isomorphic. Those subgraphs must be isomorphic. I am not saying that every subgraph of this is isomorphic to the other subgraph of G2. I'm not saying that. Here I'm considering all degree 2 vertices. There also I'm considering all degree 2 vertices. I'm constructing the subgraphs. If the original graphs are isomorphic, then definitely the subgraphs must be isomorphic. Okay, since the subgraphs are not isomorphic, now I'm going to say that the original graphs are also not isomorphic. So in terms of subgraphs also we can discuss this isomorphism. Okay, similarly, let me see what is the subgraph given by degree 3 vertices. So degree 3 vertices, one you can see you will get a box like this, and in another one the same thing. I mean, you'll find a line here and a line here. That's it. Okay, in G1 you'll get a closed box, whereas in G2 it's not. All right. So I hope you understand what are subgraphs. Okay. Now let me move to a path of length n. So let me introduce. Let's say you have a graph v comma e. Now I'd like to define a path of length n. So a path of length n is nothing but, let's say, okay, it's better to take a graph to explain this. So let me take this graph. So we are talking about undirected graph first. We can define a path of length n in directed graph and also in undirected graph also. Okay, first let me talk about undirected graph. So here you can see that starting at a vertex A, and you can reach the vertex C via two edges. So you can travel along edge 1 first, and next you can travel along edge 2. Okay, therefore from A to C, I can say that there is a path of length 2. Okay, and one more thing you can see, from A to C there is one more path available. What is that path? You can actually travel first A to B, and then you can travel to D, and then you can travel to C. So total how many edges you travel? So this is first edge and second, third, total 3 edges. Therefore this is a path of length n, of length 3. Okay, now not only these two paths, there are many paths from A to C. I can give you a path of length length 4 also. Can we have a path of length 4 from A to C? So this is how this is what I'll do. First I'll go to A to B, all right, then I'll go to B to C, then I'll go to C to E, and then come back to E to C. Okay, now this is a path of length 4 from A to C. Even though initially you reached C, and again I'm just going to E, and again I'm coming back to C. My journey is ended like this, starting at A and ending at C by revisiting C again. Okay, so let me write the definition of path of length n. So this is the definition for a path of length n. So the sequence of edges we take as a path of length n. If you travel along n edges. Okay. So in a simple graph, we can even denote the path with the vertices also. For example, the graph is simple. Let me say this E1 is the edge which is in between x0 and x1. I can assume this U is nothing but x0. Okay. And next, E2 is an edge between x1 and x2. So E3 is an edge between x2 and x3, and so on. Finally, En is an edge between xn minus 1 and xn. So in where xn is going to be b. Right. In terms of vertices also we can denote a path in a simple graph. This is what in a simple graph. Because if it is a multi graph, denoting with vertices is not good. Because if there are more than two edges between two vertices, then we need to decide along which edge we need to travel. For example, from C to A, from C to E, if there is one more edge like this, we need to decide whether to travel on the bottom edge or the top edge. Or the same path can be represented in another way also, in terms of an alternating sequence of vertices and edges. For example, you started at x0 and you're traveling along edge 1 and you ended on x1, and then you travel to edge 2 and come to x2, and then you start at x2, you travel on edge 3 and come to x3. So like this we can represent an alternating sequence of vertices and edges. This way also you can represent the path. Okay, but the better way is just represent the edges. That is enough. Okay, so now let us define what a circuit is. So a path is a circuit if it begins and ends at the same vertex. So if it begins and ends at the same vertex, then we say that the path is a circuit. It means here x0 and xn will be same. Okay. Okay. So now let us see an example of a circuit. So in the previous graph, so let me take the same one. So here can you see a circuit? It means a path which is starting at a point and ending at the same vertex. For example, first you start at A and come to B, and B you come back to A. Yeah, that also we can say it is a circuit. Okay. Or you can start at B. For example, here you can start at B and you can travel on this edge, and then you come to C, you travel on this edge, come to D, travel on here, then come to B. Alright, now clearly this is a circuit. The circuit B, C, D, B. You're starting at B and again you are ending at D. So this is a circuit. And even you can start at A, B, right? Then you go to D and then C, B, E. So this is also a circuit. Now let us define what a simple path is. So we say a path is a simple path if no edge is repeated in the path. Okay. So we say a path or a circuit is a simple if it does not contain the same edge more than once. So in this example, suppose if I take this path that is A. So since it is a simple graph, I am simply denoting with vertices. Okay. So I'm not naming the edges, I'm just denoting the path with vertices. So that is A, B, and then to C, D, B. Is it a simple path? So I'm taking a path which is starting at A and ending at B. So is this path simple or not? Yes. But B is repeated twice, no? Here B is repeated twice. Isn't it a problem? The edge is not repeated, yes. So here vertex is repeated but not the edge. So the definition is, so edge should not be repeated. One edge it should occur at one time only. Okay, but when it comes to vertex, we do not have that restriction. So for example, here you see that the edges are AB, this is edge 1, and next edge is BC, and next edge is CD, and the next edge is DB. So total 4 edges. This is a path of length 4. Can loop be a circuit? Yeah. It satisfies the definition, though. Starting at A and you are coming back to A. That's it. So we can take that as a circuit. Alright. So now here edge is not repeated. Therefore, whatever path we mentioned here, so this is a simple path. This is a simple path. I'm writing path instead of path. Okay. So now, what if I extend this length to B to A? I'll take the same sequence A, B, C, D, B, and then I'll come back to A. Now this is a circuit because starting at A, ending at A, no? So this is a circuit. So is this a simple circuit? No, this is not a simple circuit because the edge AB, yeah, and the edge BA. So this is not directed edge. Therefore, we'll treat these two as same. AB and BA will treat it as same. So this edge got repeated. So this is not a simple circuit. Okay. So now I'll give you a path. Tell me its length. You may not like the same guy every time, right? So okay, let's take something different. Okay, so let me take this. Now I'm taking the path A to D. I'm taking a path from A to D. So now what is the minimum path length? Minimum path length from A to D. Some are saying 2, some are saying 3. It is 2, no, because you can go from A to F and then F to D. Only 2 edges you need to move on. This is 1 and this is 1. That's it. Okay, so minimum path length is 2. Alright. So when you say a maximum path length, if you say maximum path, then it won't make sense, because when I say it is a path, you can repeat the edges. But if we say a simple path, then you're not allowed to repeat the edge. So now I can ask about maximum length of a simple path from A to D. So now this is my next question. What is the maximum length of a simple path from A to D? Seven? And I don't know. I need to check it. So if someone can get more than 7, then we say it is not 7. Okay, let me just see. First, I'll go along this edge. Then I'll go along it. No. So I'll go along this, then this. All right. Then I'll go back F to A, and then A to G, then here. All right, and then to here, and from here to here, then to here. Okay, that's it. So how many I got? 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 here. You're saying 7. But can you go in another way so that you can even cover the edge between BG and ED? I hope you may find some puzzles in YouTube, right? I mean, starting at same point, you need to end that point by traveling all edges, or you need to completely draw that cover all edges. Yeah. So I found 9. So can anybody come up with 10? A simple path of length 10 from A to D. I didn't make use of FD, ED, and BG. These are the 3 vertices I didn't use. All right. Anyway, you work it on it. So as of now, we found uh, a simple path of length 9 from A to D. You see, is it possible to have a path of length 10? I don't think so. All right. Okay. So can we have a path of length 0? A path of length 0? Suppose you are at one vertex A, okay, and you are just there. That's it. You're not moving anywhere. So A to A, what is a path? If you have an isolated vertex, it is possible that we can say from A to A there is a path of length 0. It means no need to travel. You just sit there. You're at A, so to reach A, you just sit there. No need to move. No need to travel anywhere because from A to A we have a path length 0. Okay, but in case of having an edge like this, A to B, you can actually travel from A to B and again you can come back to B to A. That is different. Okay, a path of length 0, it means you are at that vertex. That's it. You are not moving anywhere. That's what we mean by a path of length 0. Okay. Now let me take some interesting graph here. This one. What if I take A, B, C, G, D? Is it a path? After G, next D. Is this a path? I'm writing a sequence of vertices. Is this a path here? Yeah, no, it's not a path. Why? Because from A to B we have an edge, B to C we have an edge, and C to G also there is an edge. But from G to D there is no edge. Therefore, it is not a path. Okay, so given a sequence of vertices, we can identify whether it is a path or not. All right. Okay. Now let us discuss about connected graphs. When do you say that a graph is connected? Okay. So we say that a graph is connected if there is a path between any two distinct vertices. Okay, so if a graph is said to be connected if there is a path between every pair of vertices of a graph. For example, these are all I can draw now. So let me take vertex. So is this graph connected? Not connected. Why? Okay, let me name the vertices: A, B, C, D, E, F. Okay, give me two vertices so that there is no path between these two vertices. Okay, what is the definition of a connected graph? When we say graph is connected, I did not say that there is an edge between any two vertices. That is actually a complete graph. Don't get confusion between a complete graph and a connected graph. A complete graph, it means there is an edge between any two pair of vertices. But a connected graph, it means there is a path between any two distinct vertices. Okay, now you tell me, is it connected or not? Yeah, so this is connected, isn't it? So this is a connected graph. Why? Because between any two pair of vertices, I can always find a path. From A to F, if you ask me a path from A to F, yeah, I'll give you A, C, E, F. This is a path from A to F. And if you want a path between A and B, all right, A, C, D, B. Okay. So now I hope you can even go from F to D also. What is the path from F to D? That is F, E, C, D, B. So between any two pair of vertices there is a path. So therefore it is a connected graph. Alright. So a complete graph is always connected. A complete graph is connected. Okay. Moreover, we can say that there is a strong connection if it is a complete graph. Alright. Now let me draw another graph. Tell me whether is it connected or not. Now is this graph connected? Let me denote the vertices. Yeah, that is A, B, C, D, E, F, G. Yeah. Oh, many no's. Alright, you are saying that this graph is not connected. Alright. If it is not connected, then you tell me two vertices so that there is no path between those two vertices. GD. Yeah, there are many vertices you can give. You can take AE, right? So here, suppose if I redraw this graph, so I can draw it like this by keeping vertices in different order. So A, B, you take C here, and I'll take G here. Okay. So this is one graph. From A to B, there is a path. From A to C, there is an edge, and B and G are incident. Okay, next. We can draw it much better by taking G upside. You take G here. B to G and A to C. This is one. The other one, so let me denote the vertices D, E, F. Alright. So now the edges are this. So now I can rewrite this graph into two separate parts, two separate connected graphs. Okay, so the original graph is not connected. Now I'm going to say that this original graph has two connected components. Okay, now we need to define what is a connected component. Connected component of a graph. So a connected component of a graph is a connected graph that is not a subgraph of another connected graph. Try to understand. A connected component of a graph is a connected graph. Let me write. All right. I hope you can see that. A connected subgraph which is not a proper subgraph of another connected graph of G. See, for example, here we have this graph, right? Now, if I take, if I take the original graph into two parts, one is part G1. So this is G1, and whereas this is G2. Okay. Now, if you see the entire G2, this is connected. Okay, and it is not a proper subgraph of some other component here. Do you understand? See, for example, let me do one thing. Let me take just E and D. If you take ED, this is connected, right? ED is connected, and this is a subgraph of this connected graph, that is G2. Okay, now I can't call this ED is a connected component. This is not a connected component. Okay, similarly, this BAC, is connected, but it cannot be a connected component. Why? Because it is a subgraph of connected graph, that is G1. Do you understand? In other sense, we can say the maximum connected block. That is what we meant by a connected component of a graph. Alright, so there are two connected components here in this graph. Alright, now let me take some other graph. I think I'm making the thing so complicated. Alright, so is this graph connected? No. You can clearly see how many connected components can you see here? Yeah, two connected components, right? So let me name the two connected components. Let me assign the vertices names A, B, C, D. This is one component. The other component is E, F, G, H, I. Okay, so you can see two connected components here. All right. Now, when do you say that a graph is disconnected? The definition is so simple. What is the definition of disconnected graph? It's easy to say, yeah. A graph which is not connected, that's it. A graph which is not connected is a disconnected graph. Alright. So a disconnected graph will have either two or more connected components. Okay, if you say a graph is disconnected, definitely it will have two or more connected components. And those union will be G, the graph G. Okay, I think I did not discuss what is union of two graphs. What do you mean by union of two graphs? For example, you have, I mean, you can take this as G1 and you can take this as G2, the subgraph. I'll say that the original graph G is nothing but G1 union G2. That's it. Okay. Whereas, for example, let us take these two graphs A, B, C, D. Now I'm taking one more graph A, B, C. I don't want to take D. Alright. So there is an edge between AB and BC. If you assume that this is graph G1 and this is graph G2, okay. So now what is union of these two? G1 union G2 is nothing but the graph given with these four vertices A, B, C, D, right? So you write all edges in G1 and also all edges in G2. That's it. So this is the union of those two graphs. Suppose if I have a few more vertices here, okay, I'm going to write those vertices also. If I name it as D and E, then the union you can find A, B, C, D. Okay, so this is what we meant by union of two graphs. So if a graph is disconnected, then definitely it is union of connected components. So how about a null graph? For example, if I take a graph of this type, right? This is clearly disconnected. This is a null graph. Okay, this is disconnected. Now, how many connected components are there? Yeah, 5 connected components are there. Because from that vertex to that vertex, we have a path that is of length 0. We have a path length 0 from A to A, even from B to B. Similarly, from every vertex to the same vertex, we have a path length 0 here. Okay, so this has 5 connected components. Okay, now let's discuss an interesting topic about these connected graphs. Okay, those are cut vertices and cut edges.